Okay, in the last few times, we've been talking about what goes on in ionic solution, and we saw that one of the most useful ideas is the idea of electrostatic potential or electrical potential. We saw that potential is energy, usually energy of interaction per unit charge, and it controls or allows us to understand the attractions and repulsions between charges in solution, but also between an electrode stuck in solution and the charges that happen to be there, or the any other surface that happens to have a charge that's stuck into solution. We saw that one of the consequences is when the ions are mobile, are able to move under the effect of or influence of a potential, then they create these counter-ion atmospheres which screen all the charges. So if you look out in bulk solution, you don't see any electrostatic potential because all the electrostatic potentials have been screened by counter-ion atmospheres. Only if you look real close to any charge or surface do you see an unscreened electrostatic potential or electric field. We'll see as we go through today's stuff that screening phenomenon is really important for understanding the main topic of today, which is electrochemistry. So everybody knows, I think, that you can stick two electrodes in a solution. So over here, you've got a type of simple electrochemical cell. You've got an ionic solution of some kind. You stick two electrodes in there. The most common case that people normally know of is where you stick two electrodes just in a water solution, and then you apply some voltage here, and you'll create hydrogen at one electrode and oxygen at the other, and that's a redox reaction, right? You're creating hydrogen and oxygen from water, which is a redox reaction. And it's being driven by the applied voltage that you put in from outside, and so it's clear that there's some very close connection between electrical phenomena and chemistry. There, you can start a chemical reaction going by applying a voltage from outside, and that's what we want to understand. So before we go any further, let's just talk about the fact that there are two basic generic kinds of electrochemical setups. The first one is the one I've drawn already, where you've got both electrodes in one pot, and you apply a voltage, and the reaction starts to go down here. But now you're creating both reactants and products. So at one voltage, so let me just say, yes, let's be clear. At one electrode, there'll be oxidation taking place. Oxidation. And at the other electrode, there'll be reduction taking place. And so there'll be some oxidation reaction products coming off of this electrode. There'll be some reduction reaction products coming off of that electrode. But then they can mix in the middle, and if they're inclined to react, as they usually are, then they'll re-react, and whatever you create at this electrode and whatever you create at that electrode will just get re-destroyed in the middle. And so there's usefulness to this kind of setup, but it doesn't allow you to build up reactants and products. It doesn't allow you to set things up really with as much control as you'd like. So the other type of setup is that you've got two pots and a salt bridge in between them. And we'll talk about that salt bridge in a second. It plays an important role. And then you've got your two electrodes, still only two electrodes, but now one in each separate pot. And you apply a voltage, let's say, and that builds up some oxidation products on this side, some reduction products on this side. But now because they're in separate pots, they can't mix, and so you can build up whatever concentrations of reactants and products that you like, and that allows you a lot more control. You don't have this uncontrolled reaction going on in the middle. So mostly we'll talk a little bit about this cell, and mostly we'll talk about this kind of cell as we go down. Okay, but in either case, it's clear that you can drive a chemical reaction like electrolysis over here with an external potential. And we also know that if you have a battery setup, which basically is a cell like this running on its own, then you can also create a potential, a voltage, or a current. And anyway, you can create electrical power with a chemical reaction. So that means that there's some close connection, very close connection as it turns out, between chemistry and electricity. And we call that connection electrochemistry. And the purpose of this chapter is to try to understand that at a deep level, a deep enough level so we can actually do some calculations. The core for understanding that is to understand that there's almost no difference between this electrostatic potential that we've been talking about and the chemical potential that we've been talking about all semester. In fact, here's the relationship over here. This is the chemical potential, and this is the electrostatic potential. And you can see that the way I've written this anyway, the electrostatic potential is just a contribution to the chemical potential. In fact, all this stuff over here, this and this, are just the normal terms in the chemical potential. Normally, this electrostatic contribution would be buried inside of this standard state chemical potential. Now I've broken it out. And so the only difference between chemical potential and electrochemical potential, as it's called, is just that we've broken out and we're now paying attention to the contribution from the electrostatic potential. In most chemical situations, there isn't any electrostatic potential to worry about, but in electrochemistry and in ionic solutions, both, you do have to worry about it. And so we break it out and pay attention to it in our equation of state for the chemical potential. Now, why is there a contribution from electrostatic potential? What's the physical reason for the chemical potential to be affected by the electrostatic potential? Well, the basic reason is that electrostatic potential is a measure of the work that's been done on charged particles. And in ionic solutions and in redox reactions, electrochemical reactions, there's nothing but charged particles, right? There's all these ions running around in solution. There's also, in a redox reaction, all kinds of electrons being transferred from one place to another, and electrons are also charged particles. So it's very clear that if you're moving charged particles around, you're moving them closer and farther to each other, some of them are positive, some of them are negative, there's going to be work, there's going to be interaction energies, and the electrostatic potential is how we keep track of those. Here's an illustration of that down below. I have some source of electrostatic potential. That source might be an electrode that I stick into solution, or it might be other charges in solution or some other surface or anything that has charges on it or can be charged up from outside. That's a source for the electrostatic potential. Now I've got an ion far away. I start bringing that ion in close. As I do, I'm going to bring it into the region where the electrostatic potential is non-negligible. And there will be forces acting on that charge all the way along as I bring it in, either opposing, pushing the charge away, or attracting it, pulling it in. Either way, there's going to be work done by this electrostatic potential, by these sources really, on this charge as it moves into its current location at some distance from the sources. That work can be reversible. If we do the process the right way, it can be reversible work, and we already know that reversible work, non-PV reversible work, is Gibbs free energy, or that's one way to think about it anyway. And if I take Gibbs free energy per mole, then that's chemical potential. So it's clear, just from this alone, from the fact that we're doing work, that we're changing energy, that it's going to affect the chemical potential. And we'll see down below a little bit more clearly exactly how that works out. All right, and if we're in an ionic solution, then what that means is that the chemical potential is high in a region where the charge, either on an ion or on an electron, is being repelled by the local chemical potential. So if I have a positively charged electrode here, electrons are going to be attracted to that, right? Because they have negative charges. Negative ions are also going to be attracted. So the chemical potential for the electrons, the chemical potential for negative ions is going to be lower in this region near the positive electrode. On the other hand, a positive charge, the chemical potential for a positive charge is going to be higher because it's repelled by this positive electrode. And everything is also true on the other side. By the negative electrode, the positive ions are attracted. Their chemical potential is lower out there. The electron chemical potentials are higher in the neighborhood of the negative electrode. And the negative ions, on the other hand, also have a higher chemical potential in the neighborhood of that electrode. So when we're charging up these electrodes with our external power supply, we're creating a chemical potential in solution which can attract and repel and change the chemical potential for every charged species in solution, which includes all the ions, positive and negative, but also any electrons that might be active or moving around or being transferred in a redox reaction, for example, in the course of a chemical reaction. All right, so that, I hope, makes it clear that there should be a connection between chemical potential and electrostatic potential. We'll talk a little bit more quantitatively about that in a minute, but in the meantime, I want to say a little bit about what's actually going on inside an electrochemical cell. There's a tendency to gloss over the actual features of an electrochemical cell in most classes in chemistry, probably in other classes too, and I think it's a good idea for everybody to see at least once in your undergraduate career what's actually going on inside an electrochemical cell. So to understand that, the first thing we should look at isn't an electrochemical cell itself. We should look at a parallel plate capacitor. And so a parallel plate capacitor is a little bit like an electrochemical cell. You can see it, right? You've got two electrodes, a positive electrode over here, a negative electrode over there. You got our power supply here. And that power supply is going to charge up this positive electrode. It's going to charge up the other negative electrode also, but with negative charges. And that means that there's going to be a potential difference between the two sides. If I have a power supply that's supplying V volts, then that means that this side, it's usual convention to say that this side will be at a potential phi of V. The power supply sets the potential at this surface of this electrode at V. And on the other side, it's convention to say that the potential is at zero. Now, this zero here is a convention. The only thing that matters physically for anything is the difference in potential. So we're free to choose the voltage on this negative electrode as we like. All that matters is the net difference between these two sides, and for that reason it's conventional to call the negative side 0 and the positive side plus V. All right. If we do that, that means this space-dependent potential function has to vary between these two electrodes, right? It's got to go from V to 0, and it turns out that if you work out the electrostatics, it varies smoothly and linearly and uniformly across the gap, and so the potential looks like this. The electric field is important because it's the thing that's actually exerting forces on either the ions or the electrons. The electric field is force per unit charge, which means that if I have an electric field and I have some other thing, let's see, some charged thing, I'm out of space, over here. So if I have an electric field, here's my electric field, and there's a charged particle with charge Q in there, then the force that will be felt by that particle is just Q times the electric field. If the charge is positive, then the force will be in the same direction as the field, but if the charge is negative, so like an electron, then the force will be in the opposite direction of the field, but it will always be either in the direction of the field or in the opposite direction of the field. And you can see that it depends on how big the charge is. The bigger the charge is, the more force a given field will exert. So the electric field that's in this parallel plate capacitor is the thing that actually exerts forces on any charges that may be in this gap. And the electric field is defined to be the gradient, or in this case, the z derivative. So z is the distance from the positive electrode. The z derivative with respect of the potential. So it's the derivative of the potential with respect to z. That's what the electric field is. So if the potential is uniform like this, then the electric field is also uniform. And so there's a uniform electric field inside the gap, and because of the way the potential is shaped, that electric field is just equal to the voltage across the gap divided by the size of the gap, by the distance d between the two electrodes. And that gives you a certain value. The units for E here is volts. The potential is in units of volts per meter in MKS or SI units. And so electric field is volts per meter. And so if I have, for example, a 1 millimeter gap, pretty small gap, and I have a 1 volt potential, then the electric field in the gap, since it's uniform everywhere, is equal to 1 volt per meter. And that's a pretty small field. You need much bigger fields than that in order to do much. But a volt per millimeter, which is 10 to the third volts per meter. And again, that's still a pretty small field. You need much bigger fields than that to do chemistry anyway. It's a pretty big field for some purposes and a pretty small field for electrochemistry. We'll see why in a bit. All right, so that's the parallel plate capacitor. You can see that the important thing is that there's a field in there, and there's a potential in there, and those fields and those potentials are determined by the electrodes and the power supply, which is charging up the electrodes. Now all we got to do is fill that gap with an electrolyte. So now, not just air in the middle, but an electrolyte, which means an ionic solution. And once you put an electrolyte in there, what does that mean? Well, now there's ions in solution. The ions can move under the influence of this field, right? So this field is pervading. At the moment that I fill things, before the ions have a chance to move, this electric field is still there, acting on all the ions. It's pulling the negative ions this way, it's pulling the positive ions the other way. It's that electric field that creates the screening layers that we know will be created. And that alters both the electric field and the potential, the electrostatic potential function that exists inside the gap. And so after a very short period of time, milliseconds at most, the screening layers that we know will be created in an ionic solution will build themselves up at both electrodes. And we know what the screening layers do. They screen off, they cancel all the charges on these electrodes. That means that if you're looking in the middle here, you don't see any charge. That means there's no E field in the middle, no electric field. It means the potential is stuck at some constant value. It's not varying at all in the middle. The only place where the potential varies is right near the electrodes, where you're inside of the screening layers on both electrodes. On the other hand, the voltage difference is still V volts, right? Between the two sides. That means this must be a really steep drop right here, right? And this must be a really steep drop here, too. That means all the potential change is occurring now right close to the electrodes, and there's no potential change in the bulk solution. That means the electric fields are all confined to the electrodes. So I kind of covered it up there, but those little red arrows that you can still kind of see, that's the electric fields. They're all suppressed in the middle. The electric fields are canceled in the middle and they're all confined now just to the regions around both electrodes. Well, if we apply the parallel plate capacitor rules, that suggests that the electric field near the electrodes should be something like the voltage drop, half the voltage drop, right? Because only half the voltage drop is occurring on this electrode. The other half of the voltage drop is occurring near that electrode. So at any one electrode, the electric field should look like half the voltage drop times the distance over which that voltage drop occurs, which should be 1 Debye length, right? And so instead of dropping slowly across the whole gap, the potential is now dropping over 1 nanometer near the electrode, and likewise another nanometer near the far electrode. And that means this D is really small. This D here is really small compared to what it was in the parallel plate capacitor. Okay, if we do the actual math, that's up here. Here's the E field. We take the derivative of the potential. We know from Debye-Huckel theory, right, exactly what that potential is. And so I've written it out here for the case where we've got two electrodes like this. It's a little bit different from what we talked about in the last section, but it's pretty close. You can see the exponential decay. You can see the kappa number that we talked about in the last section. There's some extra little details that are different, but basically the same. Take the derivative of that and then evaluate right near the electrode. So we're not particularly interested in what the electric field is out here. We want to know what it is right at the surface of the electrodes, and so we evaluate at z equals 0, and you get that the electric field at the electrode is exactly what I wrote over here. It's the voltage applied divided by 2 times the Debye length. Well, Debye length is 1 nanometer, and what does that give you then? It's going to give you not, well, if that's 1/2 volt, well, let's see, let's just do it. So E then is equal to 1 volt over 2 nanometers, right? 2 times, well, 1 nanometer Debye length, let's say, and that's about 5 times 10 to the 8th volts per meter. So instead of 10 to the 3rd for a macroscopic system, this 10 to the 8th is 100,000 times bigger once you fill that very same gap with electrolyte. And that's why electrochemistry only works in ionic solutions. You need those screening layers in order to confine the electric fields to little narrow regions near the electrodes in order to get a great big E field, so that the electric field is big enough to start rivaling, or being significant anyway, to the electric fields that the electrons see inside the atoms and molecules itself. This electric field is big enough to be significant even compared to the electrons that are, to the electric fields that are seen by the electrons when they're running around inside their molecules. And that means this field is big enough to start pulling electrons off molecules or putting electrons on molecules. If the field were smaller, the energetics could all be the same. You can apply the same potential, but you just don't get a big enough field to do anything at any significant rate. All right, over on this side now, a little bit more of the details. Here's the Debye-Huckel potential. It's an exponential decay near each electrode going out to the bulk potential, which is 1/2 of V, near the positive electrode. That's what this case is. And that means that if you're out here where the screen, the counter-ion screen has canceled all the charge, then there's no electric field. And here's the calculation I just did. Electric field is, well, I wrote it here. Well, okay, so that's 1 over the Debye length. So V over 2 Debye length is the same formula, and there's the number I just got, 5 times 10 to the 8th volt per meters. Okay, so that's what's going on in solution. You're creating these Debye-Huckel layers. That's confining all the electrostatic stuff right near the electrodes. That makes them very much stronger than they would be if They were spread out. And that's why you can do electrochemistry down in these solutions. So what we're doing, of course, are redox reactions in an electrochemical cell. And in this section, what I want to talk about is what's going on at the microscopic scale in those redox reactions. So first of all, what is a redox reaction? Well, it's an electron transfer reaction. There's got to be some kind of electron transfer between chemical species somewhere in the reaction in order for it to be redox. If there isn't any such transfer, then it's not a redox reaction. It's a different kind of reaction. And the way you tell that, the formal way you can tell that, is by looking at the oxidation numbers, remember, for each of the chemical species involved, either the reactants or the products. So in this case, example down here, I've got an elemental zinc atom, or molecule, atom, and it's got oxidation number 0 because it's at its normal charge. It's not an ion. And on the other hand, I've got a copper ion over here. It's got a +2 charge. For ions like this, the oxidation number is the same thing as the charge on the ion. So in this case, that's +2. Over on the product side, 2 electrons have transferred, right? In this case, it's obvious that electrons had to transfer in order to create the +2 charge on the zinc over here and to neutralize the +2 charge that used to be on the copper ion. So now the oxidation number for the zinc is +2 and the oxidation number for the copper is 0. Redox numbers, or oxidation numbers, have changed, therefore redox. That's obvious in this case because the charges are displayed as charges on the ions. But let's look at this reaction down here. This is also a redox reaction. And in fact, 4 electrons are being transferred from the hydrogens to the oxygen, or at least formally, that's what we say. It's not really a full 4 electrons, but that's good enough. But it's not obvious. There's no charges, there's no ions. We can't see, by looking instantly anyway, that any electrons have been transferred. In order to see that, we've got to look at the oxidation numbers. For hydrogen, elemental hydrogen, the oxidation number is 0. For elemental oxygen, the oxidation number is 0 on this side. But when the two are in a compound like water over here, the oxidation number on hydrogen is +1, the oxidation number on oxygen is -2. And so the oxidation numbers have changed. Oxygen's gone from 0 to -2, hydrogen's gone from 0 to +2, and therefore, again, this is a redox reaction, even though it isn't so obvious. You got to look at the oxidation numbers to tell if it's a redox reaction or not. All right, so that's what's going on. In this case, this would be going on in the gas phase. You can certainly have gas phase redox reactions. And this would be going on in some kind of solution phase. What happens in an electrochemical cell? Well, in an electrochemical cell, you've always got some kind of electrode immersed in solution. And so things are happening at the surfaces of those electrodes. Sometimes the electrode is actually a reactant or product in its own right. So in this case, I've got a piece of zinc, which is a conductor. It can act as an electrode, but it's also a reactant. If I start out with a neutral zinc atom here that isn't charged, and then I pull 2 electrons off, say by applying a potential from above, then I create an ion by pulling 2 electrons off. That's an electron transfer reaction. That's a redox reaction. I can do the opposite thing too. I can start out with a zinc ion in solution, and notice also I've got the counter ion or dibihuckel layers shown here. I can start out with an ion in solution, and electrons can be transferred from the electrode onto the ion. Now the ion's neutral. It's no longer soluble, so it plates out onto the zinc electrode. In this case over here, this is oxidation. In this case over here, this is reduction. Reduction means gaining electrons. Oxidation means losing electrons. And so both processes can happen depending on what kinds of potentials or other interactions are happening at these electrodes. In any redox reaction, there has to always be both an oxidation and a reduction. Somebody's got to gain electrons. somebody's got to lose electrons. So an electrochemical reaction, and therefore an electrochemical cell, will always have an oxidation side and a reduction side. All right, down here it's the same thing, except I've got a neutral electrode here. So up above, the electrodes actually participated in the reactions. Down here, the electrodes are just ways of conveying electrons in and out. They're not participating themselves as reactants or products. So you've got a couple of chloride ions. If I apply a big positive voltage here, a big enough one, I can suck those electrons off into the electrode. That would create neutral chlorine atoms, chlorine radicals. They don't want to hang around as chlorine atoms very long. As soon as they encounter each other or collide, they'll form a chlorine molecule. And so you get Cl2 in solution. And that's what? An oxidation reaction, right? Because the chlorides lost electrons. The opposite can also be done, in this case again, a neutral or inert platinum electrode. And now I'm pumping electrons or pushing electrons onto an existing ion, in this case a copper 2+ ion. That neutralizes the charge. The copper becomes insoluble and plates out onto the electrode. So again, oxidation and reduction can happen in this case without any chemistry taking place that involves the platinum atoms themselves. All right, let's talk about the structure of electrochemical cells then. An electrochemical cell can be just a one-pot cell with 2 electrodes in it, like I drew above. But the more useful and maybe even more common case is to have the 2 half reactions, the oxidation half reaction and the reduction half reaction, be separated out into 2 separate pots. And the advantage of doing things that way is now, as I start applying voltages and causing changes on this side and also causing changes on this side, the stuff that's produced, the new, in this case, the new An+ ion. So here I'm pulling N electrons off of A and creating An+. Here I'm pushing N electrons onto B and creating Bn-. Those new species that I'm creating on both sides can't mix with each other, can't react with each other directly, so they're allowed to just build up in each pot separately. And that's useful. That means you can change the state of the reaction and not have it just react and go back to its original state. Again, in this case, and in all cases like this, you've got a half cell over here. Let's call the half cell over here. A half cell over here. There's always 1 half cell for oxidation and 1 half cell for reduction. There's always a reduction, an oxidation, half reaction going on in the oxidation half cell. And there's always a reduction half reaction going on in the reduction half cell. Notice, this is an oxidation because electrons are a product. We're losing electrons. This is a reduction because electrons are a reactant. We're gaining electrons. All right. Here's a more concrete example. We'll talk about this a little bit more later, too. But in this case, the way I've got this drawn, the zinc side here is losing electrons. Electrons are a product, so it's oxidation. The iron is gaining electrons. The iron is being reduced to metallic iron, and therefore it's reduction on that side. And in this case, electrons are flowing through the wire. Also in this case, electrons are flowing through the wire. And as electrons are flowing, work is being done by the potential difference between the 2 sides. Work is being done on those electrons. That's important. Work is important for thermodynamics. It's basically free energy, right? So there's a free energy difference between these 2 sides. And we will quantify that and we'll derive the Nernst equation using that fact. There's one other feature of a 2 half cell overall cell like this, and that's this salt bridge. if I didn't have the salt bridge, what would happen? So let's draw a picture over here of a cell without a salt bridge. Oh, without a salt bridge. Here's the electrode, here's the connection. It's clear that there's a problem in this case because we don't have a full electrical circuit in this case, right? We've got voltage being applied to two things that are not connected electrically, and so we don't have a full circuit. There's got to be something that completes the circuit, but why do we have to complete the circuit? Well, let's suppose electrons start flowing this way, then we're going to get charges, plus charges built up over here, we're going to get minus charges built up over here. That's making it harder and harder for negatively charged electrons to leave this side, and also harder and harder for negatively charged electrons to come into this side, right? They're being repelled by the charges that are already there. Here they're being attracted by the charges that you got to get them away from. And so to prevent that charge buildup, that's why you need this salt bridge. In the salt bridge, there's a bunch of neutral ions, let's say sodium plus and maybe sulfate minus. And that means that the sodium ions can travel this way and cancel these charge buildup over here, the negative charge buildup. The sulfate ions can travel this way, the negative ions, and cancel all the positive buildup that's going over here. And so everything stays electrically neutral at all points, at all times, and you don't get this problem. This charge buildup would stop the reaction very quickly. And with the salt bridge in there, that doesn't happen, so everything works fine. All right, so it completes the circuit, and that's the purpose of the salt bridge. All right, so with that, I think I will stop, and we will pick up the discussion of cell potential in the next video.